Jelte Fennema to present the next one.
All right, I'm Jelte, and I'm a principal software engineer at Microsoft, and I do lots of open source Postgres work at Microsoft. I'm the maintainer of Citus and PgBouncer. I'm one of the maintainers of Citus, and I'm contributing to Postgres sort of semi-regularly. So what I'm going to talk to you about today is load balancing across Postgres servers and what is a bit broken about it. And by doing that, we'll talk about read replicas, a bit about Citus, a bit about some low-level details of query cancellations and how they work in Postgres, and we'll talk a bit about PgBouncer. So first of all, most of you probably know this, but what is load balancing? Well, it's fairly simple. You're sharing the workload across different servers, and the trick is to do that, you make sure that all the requests that these servers handle, they're independent, because you don't want these servers to have to sort of talk to each other to be able to handle the requests. So you just want them to handle independent queries, independent HTTP requests. And in this case, we're talking about Postgres, so we'll talk about queries. So why do we want load balancing for Postgres? Well, also fairly simple. It's for scaling reads or writes. But why? Well, this is sort of a normal Postgres setup. You have some clients, they do queries to Postgres. You get some more users, and your application is starting to do more queries. And you get some more users, your application becomes very popular. You get more queries. And then, suddenly, Postgres can't handle all the load anymore. So Postgres needs some help. We need more Postgres servers. One very simple way, common way of doing that is read replicas. This way you send all your write queries to what's called the Postgres primary. This can handle read and write queries, but you only really want to send your write queries there. And when you write to the database, everything that is written there, because of those queries you sent, it will be copied to a bunch of other servers. These are called read replicas, and they can only serve read queries. But for most applications, read queries far outnumber the write queries. So this works in a lot of cases. You sort of have copies of your data, and you serve reads from those copies, and the writes, they go to one single server. Another way of doing it is to use Citus. And with Citus, you can even scale both your writes and your read queries. Because all the servers, they can handle reads and writes at the same time. And the way that works is the data is not actually on all the servers. The data is spread out. Like one server has a bit of data, one other server has a bit of other data. And when a server receives a query for data that it doesn't have, it will forward that query to one of the servers that does have that data. And those pieces of data, we call them shards. And there's also the coordinator, which you can do some schema changes, because you can't do like alter table or create table on all the nodes. But most of the time, that's not really problematic. One node for just all the alter table and create table, that's normally fine. There's two ways of doing this with Citus. We have row-based sharding, which is sort of the original Citus way that we've supported for many years. And that way, you have your tables there. You only have like one message table and one user table and one thread table, and those are split into pieces. And one piece is on worker node 1, so all the data for tenant 1 and for tenant 2 is on worker node 1, and all the data for 3, 4, and for tenant 3, 4, and 5 is on worker node 2. But from your application, those tables will just look like a single table. You won't see that it's split. There's another way though, and that's relatively new. It's about 1.5 years old in Citus, and that's schema-based sharding. From your application, you will actually see lots of tables, because every schema in Postgres. Schema is a way of grouping tables together with a common prefix. So you will query, like, if you want the data for tenant 1, you will query the table tenant1.message. Then you can get the messages for tenant 1. And so you will get lots of tables, and these schemas will all be split, but that does give you the advantage that you don't need a tenant ID column, which can be hard for migrating to such a sharding approach. And there's also some other benefits, like you can easily add some other table to one of the schemas. Like, for instance, you have one important customer that needs some extra table for some random data that they need, or some index because they want to search the data in a slightly different way than other customers. So you can customize your schemas this way. With row-based sharding, you cannot. But it does mean you have to manage lots of different tables, because you actually have lots of different tables. But one thing that's common across all of these approaches, both read replicas and Citus, is that the traffic that you have, all the queries, they need to actually be spread across the nodes that you have. Because if that doesn't happen, I mean, you can have like 10 nodes, but if all the queries still go to only one, I mean, what's the point? So you need some way to make sure that the load is sort of spread evenly across these servers. And there's two common ways of doing that. One is client-side load balancing, and one is server-side load balancing. And we'll talk about client-side load balancing first. The way that works is that clients know about all the servers and then choose different ones. Like, for one query they send a server to server A, and for the next query they send it to server B. For instance, like that. Or maybe you sort of split it a bit across your, some servers, they only go to server A, and some other servers only go to server B. But that brings a couple of problems. The first one is that every client needs logic to choose these servers. They actually, I mean, if they have a list of servers, they need to be able to pick one to send a query to. So it brings extra logic to the client. And many clients have this logic, like Java, C# and Rust, and since like a short time in PG16, even libpq clients, which are like the vast bulk of all the clients, like Python and Ruby, and most clients are based on libpq because that's the C library that Postgres provides. I contributed that in Postgres 16, so now libpq-based clients can also do this load balancing, but there are still many that don't. So if you, for instance, if you use Go or use like async PG, which is a less popular client than psycho-PG for Python, and that one is not based on libpq, so that one doesn't support this kind of choosing of servers. So you need to have the right clients to be able to do this. So it depends on your client. And there's another problem. Every client actually needs to know about all the servers. You somehow need to tell them what the servers are. And there's two common ways of solving that. One is you have a hard-coded list of IPs or host names, like you have server.a.microsoft.com and server.b.microsoft.com, and you sort of put them in a list, and the client picks one of them. But there's another one, and that's usually easier to manage, is that you have multiple DNS records for you have multiple DNS records for the same domain. So a domain can resolve to multiple IPs at the same time. So then you still only have to provide one host name to your client, and then the client will get from your DNS server what are the IPs matching this client, and it will get a list of IPs. So you don't have to actually specify the IPs or the host names in the config file for your application, but you can just give them one domain name that you can change sort of from the server side. And that's nice, but it does both sort of still have like a third problem, and that's like the third problem that we always run into, is cache invalidation. So what happens when you add a server? I mean, now the DNS name needs to be updated, or you need to update the list that the clients have, and you need to restart them all. So there's a lot of, there's some orchestration that you need to implement to handle these kind of things. So let's take a look at the second option, server-side load balancing. How does that fare? Well, the way it works is that instead of the clients knowing that there's multiple servers, we secretly do that behind the scenes. We pretend we're one Postgres server, but actually this Postgres server, it consists of many servers. But the client, the whole point is the client doesn't need to know about this. We handle this all at the back end. And the way that's usually done is with an off-the-shelf TCP load balancer. TCP is like this basic network protocol that everything uses, from your HTTP, from your web browser to Postgres. And there's many load balancers for this. Like your cloud provider has probably multiple options for load balancers. You can buy dedicated machines that do this load balancing. You can also have like a software load balancer that you can install on any regular machine that you have. And the ones that the cloud providers provide, and some of the sort of the fancier network infrastructure one, they use software-defined networking, which means that there's not actually a physical load balancer server, but the way your packets get routed, the network itself takes care of it. And sort of what that does is that each TCP stream is assigned to a different server. So you want all these TCP streams to be different. And that way you split it a bit. So there's a few problems with this as well. One is it costs money. Like these extra machines, these cloud provider services, they're not free. They ask money for them. And when you're not using like this fancier software-defined networking approach, like a load balancer also introduces extra latency because it's an extra hop in your network path. So if you care a lot about like latency or performance, this might be a problem for you. So why do we use this at all? Well, it's a very important reason. It doesn't require users to actually listen to their DBAs or their cloud vendors. Some users will listen, but many others, as soon as they can connect to the Postgres server, they are happy. Like their queries work, and then suddenly in the middle of the night, you get called that the database is down, and you see like, oh, only one of your read replicas is actually doing anything. All the other 5, they're just doing nothing. And yeah, then you don't really want that. So, at least as like a Microsoft person that works on like Azure, the Microsoft cloud, I just want that load balancer because I don't want to have to worry about customers not doing the exact thing that I told them to do, because I know that's not always going to happen, and I don't want to be in trouble for that. I want our customers not to have to be able to shoot themselves in the foot. But not so fast. There's one important assumption that this whole thing requires, is that different TCP streams, they need to be independent, because that's how TCP load balancer works. Every TCP stream might go to a different server. And that's not actually how the Postgres protocol works in all cases. Because Postgres supports query cancellations. And the way they work is that a client, when they connect, they open a new TCP stream, they connect to the Postgres server. They send like, I want to connect, this is my password, something, something, something. And then the server, they send back, okay, good, you are logged in. You can send me this secret token with some secret, 123, very secure, to cancel any queries that are running on this connection. And the client is like, okay, fine, I'm gonna run delete from users. Oh, oops, I pressed enter a bit too quickly. I wanted to do like a where, like a specific user only, not my whole database. So what do? You press Ctrl-C, or in PGConf, or you press like the cancel button in your pgadmin or some other GUI interface where you run queries from. And that will send on a separate TCP stream the cancel request with the secret token. And then Postgres happily says, like, okay, well, I canceled the query, no worries. I undid all the deletions. You still have your data. No need to worry. But what happens if we introduce a load balancer into this picture? Well, if you then send delete from users, the load balancer might send it to server A. And if you then cancel, the load balancer might send it to server B. Well, you might see where this is going. This is not going to work. Because server B is like, I don't know this. This is a secret token that I've never heard of before. This is probably a hacker. Let's ignore it and pretend everything is fine. But I'm not going to do anything. I'm not going to throw an error message. I'm not going to put a warning in your logs. You have no clue that this is not happening, except that all your data is still gone. So yes, there's a bit of a problem here. The important assumption that TCP load balancers bring is that TCP streams are independent. And for queries on the same session that works, you might have queries that depend after each other, prepared statements, something like that, or like a set to set some session variables. And each new session, there are new TCP streams. That's fine, because new sessions, they're separate. But query cancellation requests, they require that they be sent to the same TCP stream that the query cancellation was from. So yeah, that's what I call the cancellation problem. Our query cancellations, they can end up at the wrong server, and that happens most of the time. If you have 10 read replicas, well, only 1 out of 10 times, maybe if you sort of have a uniformly random load balancer, it will send it by accident to the right server. But actually, that's maybe not even so horrible. What do you do if the query is not cancelled after you send the first one? Well, you probably press the same button over and over and over again until it stops. So maybe that's okay. But it would be kind of nice not to have this, because in an interactive GUI or a console, this can be fine. But if your application itself actually requires these cancellations to work, then because maybe like a query is taking too long and it wants to cancel it, then it might not retry this thing so often. And it does seem kind of annoying that you have to press the button multiple times anyway. So, what can we do? Well, one idea is to make Postgres servers know about each other. So, let's sort of do the same flow, like the delete from users goes to server A, and the cancel token goes to server B. But instead of server B saying, I don't know this token, it's a hacker, let me ignore this, they're like, I don't know this token, but I mean, that probably means it's not for me, it's just for server A. Let me send it over there. And then server A can say, like, yes, good, I canceled your query, and your data is fine. But yeah, that's a nice idea, but how do we actually make that work? Postgres doesn't support that out of the box. So what can we do? Well, the first idea, as a Citus developer and developing some other extensions, one idea is to create an extension to do this. I mean, that always solves things. So that's the way how I solve problems in Postgres. I make an extension that solves the problem. But there's no hooks at all that extensions can hook into for this cancellation-related code. So there's no way you can add some custom code to handle this in a different way and to maybe forward the cancellation request to somewhere else. And getting hooks or even built-in functionality into Postgres, that will take a long time because, I mean, any change to Postgres, it will take a long time because of the way the release process works and the reviews. And and even if we got it into Postgres, then it wouldn't work on old Postgres versions. And at Microsoft, we host sort of all the supported Postgres versions. And so we kind of want stuff to work with all of them, if at all possible. So, and even if all of that was fine, and we were like, okay, this load balancing we only do for the newest Postgres version, and we spend all the time to get it in, then we still need to build all this actual cancellation forwarding logic into something, which is quite a bit of work. And Postgres doesn't know at all how to do that because it normally, it doesn't forward cancellations anywhere else. So the second idea is to modify PgBouncer. But wait, maybe not everyone here knows what PgBouncer is. So let me give a quick introduction. PgBouncer is a proxy for the Postgres protocol, a connection pooler, to be specific. And what that means is that when it gets queries from clients, it will forward them to Postgres, and it will actually try to use as little connections to Postgres as it can to do that. So it won't open connections one-to-one. So when it gets a second connection, it won't open a second connection instantly to Postgres. It will wait a bit, and once the select is finished, it will send a delete over the same query, over the same connection to Postgres. And this can reduce memory usage and CPU usage and all kinds of other problems at the Postgres side, because Postgres connections are heavy. You have this max connection setting, and it shouldn't be too high, but it shouldn't be too low, and even if you don't use all of them, it's still using resources. So that's kind of one reason to use PgBouncer. But we're not actually even going to use it so much for that purpose. What we want to do is we want to modify PgBouncer so that it can forward cancellation tokens to other places than Postgres, to other PgBouncer servers. So that's what I did. I mean, I'm one of the PgBouncer maintainers now, so I can implement this. I get some reviews from one of my colleagues or from some other people, and we have this feature. So the way it works is that if you have a load balancer, and again, this sort of same setup, instead of going directly to Postgres, you send the load balancer up to send all the traffic first to PgBouncer. So the delete goes to PgBouncer A. And that then forwards it to the Postgres process on the same node. And then, when the cancellation token goes to server B, it goes to PgBouncer B. And that's then going to forward it to server A. Again, to PgBouncer. And then PgBouncer will forward it to Postgres. And then the query is cancelled, so everyone is happy. But sadly, that's not all. Because this whole point of doing this was to make Postgres scale better, have multiple servers, make it faster than one server could do. But PgBouncer is actually not super easy to scale in this way, because it's single-threaded. So if you have one PgBouncer on a single node, that might actually become a bottleneck, and all your queries going through it. So that's also not completely what you want. So we wanted a bit better. We want to make PgBouncer scale as well. And the way that we can do that is, instead of using multi-threading, using multi-process. And that you can do that quite easily by creating a few PgBouncer configs and starting multiple PgBouncer processes at the same time. And the important thing is that all these configs, they should have SO reuse port equals 1 in the config, which is a special Linux option, and some other operating systems support it as well. What that does is it makes this annoying port already in use that you've probably seen somewhere in your career. Like you start the web server that's already running, you start a database that's already running. The second time you do that, it will not start. It will say, oh, I can't start because port 5432 is already in use. Well, this makes that error go away, but I wouldn't recommend using it for all your applications, because it does require your application to actually do the thing that you want it to. Because what happens is that the Linux kernel basically becomes a load balancer. And it will then, every time it gets a request, like a new connection for that port, it will send it randomly, or sort of randomly, to one of these processes that are listening on this port. So if you have some state, for instance, if you run 2 Postgreses with SO reuse port on the same port, I mean, one query is going to one database, one query is going to the other database. If they're not in sync somehow, then that's probably not what you want. You really want them. I mean, you will, if you write to one, you can't read it from the other. So you should only use it for these kind of stateless applications, such as PgBouncer. So yeah, now we get an even more complicated setup. Now we end up with a multi-layered load balancer. We have a load balancer that forwards it to the Linux kernel, and the Linux kernel is now also a load balancer that forwards it to PgBouncer A1. And then that forwards it to Postgres. And then the cancellation token, it goes to PgBouncer B1. That will then forward it back to the Linux kernel. And then if you're unlucky, it might go to the wrong PgBouncer. And then that PgBouncer can forward it again to the right PgBouncer on the same machine. So after taking this very long path, at some point the cancellation token got to the place where it needs to be, which is Postgres, because your query is cancelled. So yeah, that's nice, but there's one final problem that we sort of glossed over a bit. It's where should PgBouncer actually forward this cancellation token? How does it know? If you have 10 servers, it's just going to send it to all of them? That seems a bit, well, heavy. Maybe you have 100, you send 100 cancellation tokens everywhere. This fan out, it's not really manageable. So that has a quite simple and elegant solution. It's to encode an identifier into this secret token, so that based on the contents of the token, PgBouncer knows where to forward it. So instead of having just secret token 123, we will include like the identifier of A1 into this token. And based on that, we know, okay, we need to forward it to A1, and then you can configure all the PgBouncer nodes using peer ID and a peers section, because it's called peering, this new feature, or relatively new feature in PgBouncer. The peer ID is simply like a number. You give all the nodes, all the PgBouncer processes a different number, and then in the peers section, you map all these numbers to connection strings. So, problem solved. Well, if only. Because PgBouncer, turns out, it's not really a fully perfect proxy yet. It implements most of the Postgres protocol, and it implements most of it quite well, but there's still some limitations, some things that it doesn't quite do the same as Postgres. So if you really want to make, if you put PgBouncer in front, you might miss some features that you are using now. And one really big one that people were missing for a very long time is prepared statement support. This was supported in session pooling mode for PgBouncer, but that's sort of a slower mode. That's really close to actual Postgres, as close as almost as possible, but still even that has some issues that we'll cover later. But transaction pooling mode is faster, but their prepared statements were not supported. And prepared statements, what are they? Why do we want them? Well, they improve performance. They're like a nice performance improvement that's pretty free if your application, if your client or your application supports them. You don't really need to worry about it most of the time. Your queries just get faster. Because what it does is the way you send queries to Postgres without prepared statements is, well, you send it a message like run query, and then select and where ID equals 1, and select and where ID equals 1, and select where ID equals 3, and so on and so on. But what does Postgres do when it gets this query? It needs to read it, it needs to parse it, it needs to plan, it needs to think what tables are involved, how am I actually going to execute this query? So it's not just executing the query, it's also thinking about what it needs to do to execute this query. And that's where prepared statements come in. There, you basically first, you prepare a query with a little placeholder. So you would put like $1 to say like, oh, this thing I don't know yet, but all the rest, it's going to be the same every time. Because then you can sort of execute that query just like a function. You give it a parameter 1, and a parameter 2, and a parameter 3, and a parameter 99, and it will do the same thing as we saw before. But it's only parsed and planned during the prepare, because that's where Postgres already has sort of the full query. It's just like these final little things that it needs to fill in that it doesn't know. All the rest is already taken care of. But why is that difficult with transaction pooling? Why did this not work? Well, if you send a prepare from one client, P1 is the name of the statement, and we're going to do a select. PgBouncer is going to forward that. And Postgres, it needs to remember, because later you might want to execute. So Postgres per connection it gets, it will remember the prepared statements. Because prepared statements, they're local to a connection. If you prepare it on one connection, it's not gonna, you can't execute it on another connection. But if then another client prepares an update with also P1 as the name, Postgres is going to complain because P1 is already defined. But the client below, it doesn't know that. It had no way of knowing. And then when it goes away, this is another feature of PgBouncer. When a connection to Postgres is not used for some time, or it's sort of an old connection, it might throw it away and later set one up again. So the client will now send exec P1 because it still thinks like my connection to PGBouncer was still open, so this prepared statement still exists. And it's going to send exec P1. And then Postgres is like, I don't know this thing. What are you talking about? This is a new connection. I don't have any prepared statements. So yeah, that's problematic. So how did we make this work? Because this is now working since sort of 2 releases in PGBouncer. And the way we make it work is that instead of simply forwarding this prepare, we keep a cache of the prepare statements per connection in PGBouncer as well. So in PGBouncer, we track P1 equals select, and then we actually do something else. We give this prepare statement, we give it a dedicated name for PGBouncer, like a unique name. And then we prepare that on the server, and then Postgres will see like, okay, sp1 equals select. And then when the bottom client, it will do the same thing. It will send p1 equals update. That will be saved for client 2, c2, client 2, sp1 equals update, and we give it a different name, sp2. So then we prepare it on the server, and they're both there. Great. This client goes away. We wait a bit. Again, just like before, where we would get the problem. The cache on Postgres disappears. So then, when we execute, what's going to happen now? Well, PGBouncer realizes that this connection is new and it doesn't have sp1 prepared. So it will secretly, without the client having to request it, it will re-prepare this prepared statement on Postgres. So now it's there. And this time it's client 2 because it's a new client. It's like a new connection to Postgres. And then it will not execute P1, but it will send execute sp1 because that's the name it gave to Postgres. And then that also works. So yes. How do you get this to actually work? Because it's not enabled by default yet. Probably like 1 or 2 more releases sort of trying it out and fixing some bugs, and then we can enable it by default. It's by setting max prepared statements to some non-zero number. Like 100 is usually like a good thing to try. If you really have lots of different prepared statements, you might want to set it a bit higher. But in general, like 100 is sort of ballpark good number. But is that everything? Have we now fixed all of the problems that PGBouncer had? Sadly, no. There's seems always to be more problems. The closer you look at the piece of software, the more broken it seems. So yeah, there's still quite a bit of things that don't work with PGBouncer. One of those is logical replication connections. So if you do logical replication and you try to do that through PGBouncer, PGBouncer will just say, no, I don't support this. There's also some other things. You can have some connection parameters, like startup parameters that you give when you connect to Postgres, and PGBouncer doesn't always pass all of those on to the server. A lot it will, but like the most used ones it will. And there's some TLS certificate auth setups that are impossible or hard to do. If you do client authentication, like if the client has a TLS certificate and it wants to authenticate with that certificate to PGBouncer, then that's currently not. Well, it's supported in some ways, but not with the amount of freedom that Postgres gives you. And LDAP is another thing. Kerberos, LDAP, whatever you want to call it. It's another it's another thing that doesn't always. There is some support, but it's not fully featured as much as Postgres. At Microsoft, we're working on the first 3. The fourth one, it's sort of there's a PR, but the person that worked on it seems to have disappeared, so it's now a bit dead. If there's any more that you know of, please let me know, because I really am trying to make PgBouncer like a fully compatible Postgres proxy, so that everything, like you don't have to worry about it. So yeah, that's it. If there's any questions, please tell me.
Why do you want to build this architecture when we can simply go to a distributed database?
Sorry, what did you say?
Why do you want to build this architecture when to scale a monolithic Postgres instance, when we could simply move towards a distributed SQL architecture, like maybe Cockroach or maybe Yugabyte or maybe YDB that we are currently having a presentation of here?
Well,
what's the use of building this architecture in the first place, and why are we putting our efforts into fixing something that is currently broken, as you accept, and putting more and more efforts into it rather than accepting that this is broken, it cannot be scaled, and maybe it will have some more challenges, and maybe move to a distributed architecture, which apparently you are trying to fix problems for and move towards that direction, no?
So this probably actually is also an issue for YDB and Cockroach, because I really doubt they looked closely at this, because lots of people don't look at cancellations, because they sort of think they work. That's one thing. Other thing is Postgres, vanilla Postgres is really powerful. You have all these extensions, all these forks, or they generally don't have the full support of Postgres. So it's lots of use cases, they still require actual vanilla Postgres, and they want them to scale because they want some performance. And read replicas and Citus, they work very well for that. And so yeah, that's kind of, and generally these new scalable Postgres competitors, or like YDB and Cockroach, generally, and Yugabyte, generally they don't provide the same kind of performance that Postgres does if you scale it in this way. You really need a lot of servers to get the same kind of performance. They scale pretty well, but the base performance is fairly small.
I was going to tell a comedy, but I thought I'll ask a serious question. As I scan back towards your entire presentation, I don't have to, but it was, if one would, the first slide essentially started with the fact that the TCP stream needs to be uniquely identified for the cancellation problem to operate.
Yes.
So one of the things that came to mind, and maybe I'm naive on that, is if I was using the HTTP2 protocol, I get a connection, and then I can use a multiplex stream wherein the connection is already identified to just fire in a cancellation. That's how I just thought, because maybe I use H2O as the server, and that's where I can do this very easily. gRPC is what came to my mind.
Sure. So if you have multiplexing at the, so the reason cancellations are a separate stream is because you might want to cancel like a copy, which is that's like the core reason why cancellations are even a separate stream. But and that's one thing. But the thing you're asking is if you have multiplexing at the protocol level. The only one problem is Postgres doesn't support HTTP2. That's There's definitely plans or like ideas for Postgres to support a protocol that can I think there's people trying like HTTP 3 mostly. HTTP 2 is not really a good fit for this, but HTTP 3, quick, whatever you want to call it, that's generally, it's something that people are excited about, and it's something that we might want to get into Postgres, but it's definitely not there yet. So we need something in the intermediate time. And even if we did, then you still need to. Well, that would work, but you need like then your application, your load balancer is not a TCP load balancer anymore. You want a Postgres load balancer in a sense. You will still need a load balancer because you want to spread the data across the nodes, but you want the streams to stay together that should be together.
Just one question here, like, is there any way to pass the original client IP and port which can show up in PGStat activity, which is common problem with proxy?
Sorry, could you speak a bit louder?
Like sending or showing up like original client IPs and ports in PGStat activities. That's main problem with like one of the problem with the proxies like PgBouncer.
With PgBouncer, that the stats they don't match anymore.
Yeah.
Yeah, that's definitely a problem. That's true. With session pooling mode, that shouldn't matter so much. But yeah, with transaction pooling mode, you lose all this. You lose a lot of these kind of things.
So is there like, at least last time there was some discussion on Postgres side, like some proxy protocol, or like?
Yes, I think there's still some talk about that. With PgBouncer, you can at least put like the IP address of the original connection in the application name, so you can sort of track. If your applications work sort of nicely with that, you can track the IP address. You can see the original IP address in PGStat activity. But yeah, no, the proxy protocol would definitely be better. So that's definitely one thing that we kind of want.
Yeah. Okay, thanks. It will be good to have that feature, like you mentioned.
Hey, nice presentation. I have two questions. First, like adding a PgBouncer as a load balancer, right? Just for cancellation request handling, don't you see any overhead of adding proxy? Like it is a one extra hop between client and server. First question. And the second, like scaling down with SOR use port, right? I think that is that feasible to do without connection drop? Because Linux kernel don't understand that I want to stop one of the server listening on the same port. So kernel continue to distribute load between all one, right? I want to shut down one of the PgBouncer. Then is that possible without, because what happens, ACK generally received at the kernel level, and that ACK already indicate client that, hey, I'm serving your request. And if I stop that particular PgBouncer, that request may get aborted. Yeah.
Okay, so you asked two questions. Like one is like, is there any performance latency overhead of introducing PgBouncer like this? Yes, PgBouncer does have some overhead because it needs to do something. So there's some CPU overhead. Latency overhead, there's not so much network latency overhead, only sort of for the cancellation token itself, because that might go to a different server and then have to go to another one. But since cancellations are not so common, it's not super important that this latency is there. So there's some CPU overhead, yes, but by being allowed to scale in this way, you can, generally scaling out, being able to scale out with multiple servers, it introduces some overhead. And this is one of the things that it would introduce. But because you can scale out, you can, in the end, have more performance in total. And the second question is, can you easily restart one of the PgBouncers by listening on the same port? Is that sort of a nice summary? Yes, so you can stop one of the PgBouncers. There's one PR that I'm almost getting in to make this a bit nicer. to really make it possible to sort of do like a rolling restart of all your PgBouncer processes on one node, so that there's never a moment when your connections are not working. It does require some application, like your applications will need to disconnect, because like if you use the session pooling, there's really no way of sort of transferring like a connection to another PgBouncer with and keeping all the session state. So that's, yeah, so it does need some interaction from your application, but if you set up everything right, you can have like a full zero downtime restart or stop of like PgBouncer processes on one node. But that's not out yet. It's like, would be next release probably.
Yeah, hi. Hey. Thanks for the talk. I just wanted to ask, earlier you mentioned the SO reuse thing, right? And you said that it's good for stateless applications. And later you showed that PgBouncer has introduced a cache, sort of. So isn't that introducing state into a stateless application? And would that like have problems?
So yes, it does introduce a cache and there's some state, but because that state, it's local to the connection that is open, it doesn't matter. It's not like state that should be shared across different connections, because the cache is local per connection that PgBouncer receives. So it's fine.
I'll just take one last question, and then please feel free to connect with Jelte offline.
Hi. Actually, hi. Hi.
Hi, yes,
Yeah,
sorry.
okay. So actually we are using PgBouncer, okay. So what we are facing that issue is, actually if both PgBouncer as database server, both are in that same location, actually same server we are installing and everything, it is local host only. And when we are running that queries, that time it is that running via PgBouncer, it is taking more time than locally we are directly connecting to that database. So you are saying that it is faster. So first question, and the second question is, you are right now it is cache is enabled, right? So where that's stored? Actually it is that PgBouncer side it is stored, or it is that shared buffer or something else. So I want to know that it is where cache is stored, and it is SP1 and you are showing that SP1, SP2 like that. So if it is stored means how much that capable, or how much I want to set that parameters. So if parameters we want to set that if it is 10 MP like that. So I want that particular parameter for how to scale that, actually how much we want to store that cache. First, these two questions I have in my mind.
All right. So yeah, so like the first question you asked, like yes, it's definitely possible for PgBouncer to introduce some overhead. I mean, it's doing something, so it's your query is going to be a little bit slower, but it really tries to minimize that. The second question is how to tune this max prepared statement parameter, and that basically you need to set it to something larger than the amount of prepared statements you commonly execute on one connection. So if you have 100 prepared statements that are being executed sort of over and over and over again, then you would want it to set to a little bit more than that. It doesn't really matter so much if you set it to very large things, but for most applications, but for some applications it does, because if you have lots of unique queries that you prepare and then only execute once, PgBouncer will keep that cache. So that might introduce some memory growth in the PgBouncer process, but you can fairly safely set it to a very large value. If you don't actually use so many prepared statements, you won't run into issues, and you can even try like setting it to a large number and then sort of seeing how many prepared statements you're usually sending with the statistics that PgBouncer exposes. So the docs on the PgBouncer website also have some explanation on how to tune this setting. And feel free to come by like the Microsoft booth. I'll probably be there most of the time.
Thank you, Jelte, for such an informative presentation. There is just one announcement. There's going to be a lightning talk today at the end of all the presentations, so please participate in that. Thank you.